Okay, so we're going to do a quick crash course on ray tracing and everything really quick. So you can just download Blender while that's going on. Here we go. Okay, so how are movies rendered? That's what we're going to be going over. How can we get really high quality cinematic style images like these? We went over real-time rendering really quickly in the last workshop, and it wasn't like the real pipeline, but you got the gist of it. How do you do rendering in movies? Well, the answer is ray tracing. So basically, you covered it a little bit at the end of the last workshop, but the idea is you. I'll actually go over ray tracing later, but also more specifically in this workshop, we're going to be covering how you can describe materials, and is there like a universal way we can describe a material using just like a few different parameters? So is it shiny, diffuse, skin-like, the light scatter through it and then come back up, like that. And then also, some of the workshop's going to be kind of review of CC 167 and 168. So, given the usual attendance, I know many people probably haven't taken those courses. But if anyone's watching this recording, some of this is going to be a review, especially if you take in 168. But I think towards the end, there'll be a few new concepts. Okay, so let's go over how light works in the real world. Let's take a simple scene with just a light, a sphere, and a camera. How does the camera capture this image in the real world? Well, first, a bunch of photons come down and hit a surface, illuminating a scene. Some photons don't really hit anything or hit like something really far away from the camera and don't contribute much to the image. Then some of these rays are either bounced or absorbed or refracted or anything. And we get some secondary bounces, and this goes on and on and on until eventually one light ray, or maybe several, hit the camera sensor. Now, obviously this would take a while to compute. If we just simulated all of these rays, we'd have to simulate billions and billions of rays, and it would take a long time to get like a decent quality image. It's really impractical. So how can we do this a little faster way? Well, the way ray tracing works is we do this thing in reverse. We trace rays out from the camera to a surface, and then we bounce them back. We try to kind of get them back to a light source. And this way we only need to compute the color for surfaces visible to the camera. So this whole idea of tracing camera rays back to a light source is called a light transport. And there's a bunch of different light transport algorithms, or basically algorithms for tracing camera rays back to a light source. And it's a pretty important area of research in ray tracing. If you want like a really basic light transport algorithm, you can search up Metropolis light transports. But we're not really going to be covering light transport that much in this presentation. Okay, but now that we're kind of going fast through this. But now that we have like a basic idea of how ray tracing works, we get to the kind of main bulk of this presentation, which is how can we define a way to describe how light rays should interact with this object. And the way this is done is we can mathematically define a distribution, like a probability distribution of all the possible ways that basically the light ray can be scattered once it hits the surface. And this probability distribution function takes in a few different inputs like incident light angle, surface normal, which is basically the tangent direction of the surface, the vector pointing out tangentially from the surface, and some other properties. Okay, so here's what the probability function might look like for a bunch of different surfaces. For example, when a light ray hits a shiny surface, it'll be more likely to be reflected in the reflective direction, basically, around the normal. But if we hit a non-shiny surface, like a diffuse surface, maybe my camera, maybe my mouse pad or something like that, then that might have a more even distribution across all the different directions. Okay, so what if we do this in reverse as ray tracing? As we do in ray tracing, you know, the camera rays don't come from a light source, they come from a camera. Well, basically what we can try to do is we can try to multiply this distribution function of, you know, so we're doing this in reverse, right? And the camera ray hits the surface, and if we do this in reverse, there's like a bunch of different possible ways the camera ray could be reflected. It could be, you know, for a reflected surface, it could be reflected in the reflective direction, you know, and if it's diffuse, then it could be reflected equally in all directions. Basically, what we can do to get an idea of how to shade this point on a surface, assuming it's like a white surface or something, then basically what we can do is we can multiply this distribution function with the incoming radiance around the scene. I'll put something in shared notes. Okay, thanks.
Oh, sorry. I'm just editing the shared notes. I didn't mean to distract you.
Okay. But yeah, basically we can multiply this distribution function with the incoming gradients around like a hemisphere at this point. And if, for example, if the surface is reflective, then it would be like, it would be, some would be taking in more of the incoming radiance at the reflected angle. But if it was more diffuse, you know, it would be basically taking in all the incoming radiance equally around all directions. So hopefully that makes sense. I'm kind of going faster than I thought with this. Okay, but one quick thing to keep in note is that this distribution also encodes the color of an object. So for example, let's say for our diffuse distribution we had earlier, this is like assuming we had a white surface, you know, but assuming we had maybe like 3 different sets of rays for R, G, and B different colors, and we have like a green object, you know, then a diffuse green object would be taking in maybe more of the green component than its like red and blue, you know, rays, if that makes sense. The distribution also includes the color of an object. So blue diffuse object would be like something more biased to take in more blue colors, even if it isn't particularly reflective in the direction the blue is in. And arrow keys aren't working. Okay, so mathematically this looks scary, but it can basically be described using the infamous rendering equation, where basically LO is the amount of outgoing light towards like a camera or something, and LE is the amount of emissive light, you know, if the surface is at all like emitting light, which, yeah. But then the big thing we were talking about here, FR is this distribution function we were talking about that describes like these. I know we have some new people here, so I'm just kind of going over some old stuff. But FR is like this distribution function that describes how rays are likely to be scattered. And then Li is the incoming radiance of the scene, which is, you know, this hemisphere right here. And so basically, there's also like a, what's it called? It's like a fall off term or something, this last term right here. But it basically like takes into account the fact how like if a light ray is hitting a surface at a really shallow angle, you know, it won't be contributing as much to the surface as a light ray that's hitting, points directly, hitting straight on. So if a light ray at a shallow angle wouldn't be contributing much, but if it's light ray is coming down straight on, it'll be contributing more to the surface. So this is, you know, the rendering equation. Wait a sec, that's too scary. Okay, so we actually went really fast through this. I was expecting to get to the Blender way later. Does anyone have any questions so far before we get into Blender? No. Okay. So let's get into Blender. I'm going to attempt to open it. If my laptop crashes, you know, just wait for me. I'll be back. Okay, so what is Blender? Second code is render. It's in the shared notes. Thanks, Bryce. Okay, so Blender is basically a free and open source 3D creation suite. It supports really a lot of things for a free piece of software. You can do modeling, rigging, animation, simulation, rendering, compositing, motion tracking, video editing, and 2D animation. It also has a very small game engine. And all of the software is really nice. It's open source. It actually has like a surprisingly nice GUI. It had an update recently, and it looks like a lot more modern than it used to. So I think it's actually a lot easier to use now. Okay, so let's get into some Blender. What am I going to do with these next two slides? Okay, well, let's leave this here. The slides are at like acmroll.graphics too, so if I'm going too fast and you want to like set things up right in Blender, you can go to the slides and see what I have here. But the setup is pretty simple for what we're going to be doing today. But basically, you want to set the render mode to cycles, device CPU, and then click checkmark on open shading language. Okay, so this is what Blender looks like when you first open it up. I'll be opening it up soon. But basically, there's like a few different, as I said earlier, you can do a lot of stuff with it. And so if you look at the top, you'll see like a bunch of different tabs for different window layouts for all the different workflows it supports. For example, if you want to do modeling, there's like a special layout of windows optimized for modeling. Same for like sculpting, UV editing, which is like, texture stuff. And we're going to actually be going into the shading tab later, but not right now. So basically, if you want to add a new object, you can go to this add thing right here, add button, click down, and like open mesh. I'll be adding mesh to and everything. If you want to be transforming your object, you can use these things right here. This one's translate, this one's rotate, this one's scale. I don't know what this is, honestly. Here you have a scene outline of all the different objects in your scene. In the default scene, you have like a really basic, camera, cube, light. And then here is where like the main root of everything is, or bulk of everything is. This is your properties panel, where you can change properties of a bunch of different things. Here we have render, where you can change kind of like render settings. And that's where you can change the render engine and everything if you want to do real-time rendering or production rendering. And then you can change if it's I wouldn't actually do CPU and other stuff. Output is where you can kind of change the render output if you want it to be like a PNG or the size of the image, stuff like that. And scenes, controls, these are all different things. We're going to be going to materials later because that's what this workshop is about. So we're going to be doing a lot in this tab. That's Blender. Okay, so let's get set up. Let's make a little scene in Blender. Let me share my screen. What else am I doing after this? Okay, yeah. Oh wow, look at this. Fuck. Okay, I'm not gonna be able to see the chat, so we're gonna stop this recursion. Okay, so hopefully can everyone see? I can look at a preview, yeah. Okay, so I'm gonna first remove like this point light because by default it looks kind of bad. And then I can add in like basically, I'll do like a sunlight, but you can do, actually, I'll be fancy. I'm gonna keep it simple actually. Like move it over here. Kind of rotate it and everything. And then I can like click on the camera icon right here to look at what the scene looks like from the camera. And then let me change the render settings and everything to what I was recommending. New cycle supported OSL. And then you click right here to turn on rendered mode. so you can see what the final render will look like. That actually doesn't look like. I'll give it a second. Okay. So it looks like my computer is lagging a little bit. Wait a sec. Okay, turning off rendered mode for now. It looks like my computer can't handle it. But let's say we want to mess with the scene a little bit and make it look a little better. We can like kind of change the color of our light to make it a little more sunlight. That's like that. You can kind of change the strength too. Okay. Everyone good? I think it looks like I stopped recording for a second.
Could you show us how to add like the sunlight sources? I wasn't able to figure that out.
Bryce, what was that?
Adding like the other light source that you said you'd like to add.
Oh, okay.
Yeah.
Yeah, you can do add, and then light, and then sun. And then the keyboard shortcut way to do it is like Shift A. And then also to like manipulate these, you can go to the move thing over here and kind of move it around. Or you can press G for grab. Just my computer is not taking this well. Well, you can press G for grab to kind of grab it and move it around. Okay. Yeah, let me start my screen. Here we have like basic stuff. And yeah, make sure you switch to render to get like the final rendered results. And basically, just as like you can set the material for our cube to use diffuse, which is basically what we were talking about, like a surface that's not shiny at all, and it perfectly diffuses colors in all directions. And we're going to use that as kind of an example thing. So wait a second. Back over here, and there's a rendering equation. Back over here.
Just real fast, Nick. I think Bryce was asking for you to show how to move it again.
How to move? Oh, sure, yeah. Okay. So basically, to move something. Okay. Okay, can you see? Yeah. Okay, so to move something, you just click on these things on the side. So to move something, you go like this, and you just drag each of the arrows. If you want to drag something along 2 axes, you can press this little thing right here, and you can like move it across these 2 axes. And then to rotate, you can rotate like this. And then scaling works, similarly. Is that good? You can like make your own little thing that's like not a cube if you want to. Okay, let me stop sharing. Okay. So yeah, back here, I introduced the concept of a bidirectional reflectance distribution function, which basically specifies, given like an input light ray, the distribution of possible ways that the light ray could be scattered off a surface, So if it was shiny, it would be more likely to be scattered based off, the reflection direction. If it was diffuse, it would be likely to scatter, would be more likely to scatter across all different directions. Okay, so that's called a BRDF, but wait a second. Blender calls it a diffuse BSDF, and it calls basically all of its materials BSDFs. So what's the difference? Well, basically, it's not like well defined. Like even if you go to Wikipedia, look at like BSDF, in Wikipedia admits that it's not well defined, and so like you can use it, a lot of different ways. But it's just the general idea of a combined BRDF and what's called a BTDF, or a transmitted scatter distribution. So basically, in some materials, light just isn't like either bounced off or absorbed. It's also sometimes like transmitted through the material, like maybe glass or subsurface scattering materials like your skin. And so BTDF is meant to describe that. And so BSDF combines the BRDF and the BTDF. Okay, so let's look at a simple diffuse BSDF, or BRDF or whatever. So as we saw earlier, we can define a simple diffuse BRDF as basically a constant percentage of the incoming irradiance. So we can compute the final color like so, or basically just have a color called, in computer graphics terms, called the albedo, which is just the color of the surface. And you got to make sure all the colors are like between 0 and 1. And for example, if you have like a light that's maybe like blue or so, and basically it has a bunch of different R, G, and B values, you multiply each of those R, G, and B values by the BRDF, which is just the color of the material, and also the fall-off term of is on the rendering equation, and you'll get the amount of light reflected as a result of, or the amount of light coming out off the diffuse material as a result of the light source, if that makes sense. So it's just a really simple constant term. Oh, and also if we go back to the rendering equation, I'm gonna go way back. Right here, like this term is, I explained it earlier, but I want to bring it up again. But basically, it's what's called, I forget what it's called honestly, but it basically means that as the light source comes, like the angle between the light surface and the surface becomes shallower and shallower, it contributes less to the surface's color. And this kind of fall off is called an Gaussian diffuse model. And I bring that up because maybe there's better ways to model it. Go past all this again. Oh yes. So Blender doesn't just use the constant term and the cosine, like the fall-off term, to approximate diffuse material. It uses the popular Oren-Nayar diffuse BRDF, which basically better approximates the fall-off of this, and it's pretty popular. So that's just like one quick implementation detail. You don't need to actually know its equation for this presentation, but I just wanted to bring it up to show you can have multiple different implementations or models of how a material would react. Okay, so let's do some playtime. I might share my screen again and just show around the different materials. But if you have Blender installed, I would recommend just going through the list of materials and seeing what all the different materials look like. Okay, so this is what diffuse looks like, obviously. But you could change it to, say, I would need to have some extra objects in here for reference. Subsurface scattering. Scroll. Come on. What it would look like if it had like some scattering, you know, like your skin or milk or something has like scattered to the surface. This is a model Blender has. Okay, I'm gonna stop that for now because my computer is really lagging. But hopefully you get the gist. You can have like multiple different materials and different stuff. Hopefully the photos at the bottom and the side give you a good idea of what you can do. Okay, so how can we make more complex materials? Well, basically we can use something called a shader graph. So basically, shader graphs allow you to kind of mix and modify colors and materials to create complex surfaces using textures, normal maps, etc. So if you're coming from video games, you might know that like some surfaces have their color from like a texture, and it's not just like a constant color. You can specify that with shader graphs. You can also, what we're going to do in this workshop is we're going to combine together different materials to create like a more universal material model for different materials. Because sometimes, like for example, I'll get into this later, but like your skin isn't just scattering, it's part something which I'll have you figure out, and part scattering. So like for example, damn, my webcam's off. Okay, so like sometimes light will hit your finger, or like hit like a skin-like surface, and it'll bounce off. But it also has a chance of like scattering it in. And with a subsurface scattering material, it assumes the probability of it, being absorbed like or so is constant like throughout the material. But for things like your skin, you have like a hard surface, so it's more likely to be like absorbed or scattered right at the surface than deeper inside the material, if that makes sense. Next. Okay, so shader graph. I just zoomed into my slide. I went over that. Okay, so here's like an example of what you can do with the shader graph. Here I'm being fancy and using like basically a volumetric scattering function instead of like a surface scattering function. I just wanted to show that like they exist, and they're pretty similar to surface scattering functions, except with a few differences. But basically here it can like mix two shaders to have maybe like a two-color material. So like for example, I have kind of a red inner material and a purple like outer material, and they're mixed based off the distance from the origin squared. And so like for example, the outer material would be more purple, the inner material is more red. A smarter way to do this would be maybe to like blend between colors, and then just have one like color volume and have like the blended color as an input to the volume material. But I just wanted to show that you can like mix two shaders as well, or materials as well. And like one pro of this is you can kind of like vary the densities of the volumes as well that you're mixing between. So that's pretty cool. But yeah, just keep in mind, I wanted to do volume because it's fancy, and I just wanted to show you could do that as well. But you can also, and what you will be doing pretty soon, is mixing shaders with materials. Mixing surface shaders, sorry. Okay, so yeah, let's make our own shitty DIY combined VSDF. I know if people wanted the profanity to put me down, but whatever. Basically, what I just explained, the default subsurface scattering VSDF assumes the object surface and interior is all one color. But that's not true for our skin, which has like a tan surface color and a red subsurface color. So like, you know, if you put like a flashlight to your skin, that's why the scattering is like red colored, you know. So let's just, if you don't have Blender installed, then it's gonna be kind of boring for you. But if you do have Blender, let's just do a quick factors example of what can we like mix and add together to create, what kind of shaders can we mix together to create this kind of material. I'll give everyone like 5 minutes. Oh shit, let me pause the recording. Find like a red subsurface scattering. Oh, thanks for starting the recording. Yeah, so basically the idea is if you have a red subsurface scattering material and you combine it with maybe like a diffuse BSDF, you can get like a pretty accurate model of skin. Nice. So I mixed it. So you can kind of control how much of the light gets immediately kind of reflected off the surface and how much goes into the skin. Like kind of controlling how much you mix it. Pretty nice. This is, I think, like just a simple 50-50 mix. Okay, so this is kind of an optional slide. It looks like we have some time, so I'll go over this. Basically, you might notice that like the subsurface scattering material isn't like really listed as a BSDF in Blender. But basically that's because it's what's called a BSSRDF. So this is just like a lecture of progressively longer acronyms. But basically this BSSRDF encompasses the idea that light doesn't leave exactly where it hit the surface. It sometimes, as you can see in the right photo, like goes in and then scatters around the surface and then comes out. And basically the way we can model this from the camera's perspective is that we can, you know, trace the ray from the camera to the surface, and basically we can pick a bunch of points around the hit surface and calculate the, you know, the same rendering equation at those points, and then based off like maybe, you know, the distance to the camera, the camera ray hit point, we can calculate maybe how much fall off there should be, you know, or how much the how much that point would contribute, I guess, to the camera's point, if that makes sense. So more specifically, like mathematically, in the rendering equation, we integrated over the incoming radiance of like a single point, but for BSSRDF, we also need to integrate over the incoming radiance of the points around the surrounding area as well. So, any questions on that? You need like another explanation? Okay. So, what we just did can be like more generalized, you know? Maybe we want a better model that's not just for, you know, like diffuse, combined like diffuse subsurface scattering surfaces. Maybe we want it to be like it's shiny or something as well. Or maybe you want it to have like multiple layers or something. You want it to mimic it being multiple layers. Or we have like maybe a diffuse surface underneath like a shiny coat, like maybe a car paint or whatever. How can we, you know, combine all of these materials into maybe a nice universal model? Well, basically that's what Disney did. they created what's called the Disney Principled BSDF for all of their artists. And it basically describes the material for nearly all the surfaces in any of the Disney Animation Studios movies. So they developed by Brent Burley at Disney Animation Studios as a universal and easy-to-use way to describe most surfaces an artist would ever use. So there's like a few goals he had in mind. Basically, there's this thing called like the Merle 100 or 500 dataset. It's basically just a dataset of a bunch of different material types of like varied kinds. And he wanted to create a model to model these materials as accurately as possible and with as few parameters and easy to understand parameters as possible. And there's like a few other specifications he had too, but I can't remember. Those are like the big ones. And it's now like pretty much standard in a lot of different renderers, even though it's like a Disney thing, you know. You can find like an implementation, I think, in RenderMan. It's in Blender, obviously. It's in a lot of things. So yeah, it combines a lot of previous work on approximating surfaces and a lot of modifications to existing models. So it's sometimes like blend between, you know, different diffuse models and then like add on to other models and stuff like that in order to fit all these materials. So anyway, this is what like the different parameters look like. So here we have like a subsurface parameter, which kind of changes how much subsurface scattering there is. Metallic, honestly, I don't understand most of these for some of these parameters, but like some of them are pretty intuitive, like roughness, you know, as how rough the material is. Some other things like if you want a shiny coat, stuff like that. And then this is how all the different like BSDFs and BRDFs are combined. And then there's also you know, clear coat and I think sheen lobe, which are I think both additive on top of what you see here. So some are mixed, some are added. Yeah. Okay, so if you thought that was fancy, that's what Disney Animation Studios does. This is what Pixar uses to define all their surfaces. This is called Pixar Surface BXDF. They don't mess around with any of the silly BRDF, BSDF, BSSRDF acronyms. They just call it a BXDF. And for some reason, their artists want this. And you'll find this is a recurring theme with Pixar. They like to just go above and beyond. Okay, so we're actually kind of nearing the end of this presentation. This is going fast. So basically, we went over shader graph, which is, you know, a nice node-based way to represent stuff. And basically, there's a programming language, or more like a shading language, not entirely a programming language, called OSL, which was originally developed by Sony Pictures ImageWorks to describe materials, lights, displacement, and pattern generation. So we're going to use it to describe like materials, but it can also just keep in mind it can be used for lights. There's different like shader types, I think, and stuff for doing different things. But basically, it's also node-based, just like you saw in Blender, where you know that maybe there's a function that has some inputs, some outputs, and you can kind of like attach those nodes to make a really like easily configurable system. Basically, OSL is used in a wide variety of animation VFX, including most recent Marvel films and Pixar films. OSL is also node-based, yeah. And Blender's nodes can be converted to OSL nodes under the surface by checking the open shading language box and render properties. So I had a slide on it earlier to like tell you to check that box, but that's what enables you to use OSL. And basically, Blender supports allows you to custom make your own OSL nodes. I think if you go to like add and then script and then new script or something, and you have to like make sure you have the text editor open. And Blender has a special like text editor window. You can kind of code your own custom shader. So it would make, you know, maybe you go like way back here. You could like do more complex blending between different materials, or if you like, for example, even just a simple bit of math, like computing the distance between like a point and the origin squared requires like 3 nodes, and it takes up a lot of space. And if you want to do like any more complex math, it gets really heavy really quickly and it's hard to understand. So sometimes it makes more sense just to like convert maybe a computation like this, or maybe like remixing shaders like this into an OSL node. Also, like I couldn't find like a square root function, so that's why it's distance squared. And that's good enough. Go back. Okay, so this is what an OSL script looks like. This is a really basic one. Basically, you define like a function, which takes in some inputs. Like for example, this is a really simple diffuse material. And it's basically the diffuse node you can already use, except it doesn't have like reference or anything. But basically, you have like a function name and everything. And there's different types in OSL just to make manipulating things like pretty easy. So there's a color type to represent a color, obviously. There's a vector type to represent a direction or a point or whatever. And then the big thing OSL has is what's called closures, or specifically like closure colors, where basically no calculation is actually done in this shader. Instead, it returns a closure, which is basically like a function that can be run later at the renderer's convenience. So here we have a closure color, which is a closure, like a function that returns color. And then you can kind of do like these like weird adding things. So by default, we specify it as like a diffuse model. For some reason in Blender, you need like default parameters and all these things. But we reset the SDF or the output the SDF to be the diffuse, incoming like diffuse, using Oren-Meyer, I think, model, or Oren-Meyer model, multiplied by like the color to get what it should be. And diffuse actually returns a closure as well, a closure color. And when you're multiplying color, the diffuse underscore color by the closure, it just kind of adds onto the closure as more code. And it looks weird, but hopefully it's intuitive. And that's just a really simple shader. If you want more information, there's a really nice tutorial here. I originally wanted to like cover more OSL in this, because this is like supposed to be a programming club. We're barely doing any programming in this. But yeah, I would recommend looking at this. Oh, is that really the last slide? Okay, this is a short workshop. So for the future, I would recommend taking CSE 168. I kind of gave like a really, really basic like layman's explanation of all this stuff. And CSE 168 really goes like way more in depth. And I'd recommend taking it. It's kind of hard to take though, because you have to take CSE 167 before it, and then CSE 100 before that. So if you're not if you're not a underclassman or upperclassman, it might be kind of hard. But yeah, a lot of this presentation is based off a GTC 2020 presentation on Pixar's XPU rendering pipeline, which is basically Pixar isn't using it in production yet, but basically they're working on a system where they can render images on both like a GPU and a CPU, and they're trying to get the difference between the images to be like as small as possible, and they're just working on making it like really scalable as well. I would recommend checking it out. It's actually surprisingly pretty beginner friendly. So some of the presenters, are pretty smart, and they might say some complex terms, but they do, actually go over like what ray tracing is again and everything, and it's pretty nice. And you also see that I probably kind of stole a lot from their presentation. And if you're also interested in learning more, I'd recommend checking out Ravi Ramamurthy's YouTube channel. He's one of the big computer graphics professors here at UCSD, and he's pretty well known for like a lot of his different computer graphics work. And he has like a YouTube channel. I didn't have enough time to like copy and paste the link into these slides, but you can just like you can YouTube search Ravi Ramamurthy. And he's been like posting a lot of lectures recently because everything's online now. So I would recommend going through it if you're interested. And also, if you're interested in computer graphics, I would recommend checking out this graphics interest forum. As some of you may know, ACM is thinking about starting some suborgs next year for design, cyber, maybe some other things as well. And I'm trying to start up a graphics suborg if anyone's interested, though it might be delayed because of everything happening right now. But if you're interested, please fill out this form, acmroll.com/graphics-interest. And I'll try to get back in contact later in the quarter. So yeah, these are some slide references. Yeah. If you're interested in reading like a more complex research paper, Pixar gives like a kind of basic overview of its pipeline here and in this presentation. But I would also search up, I forget what the exact paper is called, but like Disney Hyperion's render, which is also like a competitor. It's a lot simpler than Pixar's XPU, but it's also like pretty interesting in how it organizes scenes that are like maybe hundreds of gigabytes to efficiently render those scenes. But yeah, thanks for coming. That was fast. And this is the last workshop, so any questions? Okay, cool. I'm going to stop recording.